Okay, now we are on Chapter 4.2, Contingency Tables and Joint and Marginal Probability. We'll also be going into conditional probability today as well. So we're going to start with these contingency tables. And a contingency table is, let's look at this handedness data that we had before. Okay, a contingency table is where we have two variables. So up till now, we've talked a little bit about univariate data. Now we have what we call bivariate data. You can have more and have multivariate data as well. And in the case of a contingency table, it is a frequency table for two, usually qualitative variables. So you'll notice these are both here. This variable right here is called gender. And then we have a variable here we're going to call handedness. Each one of these variables has two possibilities. Gender can be male or female. Handedness is right-handed or left-handed. So what we have is a contingency table because we have the frequency of each one of these. And down here we make our totals. So we have 8 males, 18 females, 26 total, 21 right-handers, 5 left-handers, and 26 total. So you'll notice these all add up to this bottom. Now, if we go and we divide this contingency table by the total number that we have, 26, we're going to get what we call a joint probability table. And what that allows us to see is automatically, just from this table, we can see most of the probabilities that we probably need. We can see the joint probabilities are inside. So they're inside where I just drew this right here. So joint probabilities are the same probabilities are the same as intersections. So for example, if I wanted the probability that somebody was right-handed, intersection male, that probability would literally be the intersection of male and right-handed, or 0.23. So I know that 23% of the people in this class were right-handed males. So that is the joint, and all of these are different joint probabilities. So we have right-handed males, right-handed females, left-handed males, left-handed females. Now on the outside, in the margins, if you will, we have the marginal probabilities. These are the probabilities of one level of one variable without regard to the other. So we don't care what level the other one is on. If I wanted the probability somebody was right-handed, it would simply be 0.81. If I wanted the probability that somebody was a male, it would simply be 0.3. So I don't care anything about their gender in this case. I don't care anything about their handedness. Whoops, that should say probability, not R. It should say probability of N in this case. So that's where we get a contingency table and a joint probability table. So let's take a look at an example of this. And let's talk about the TV example. So there are 4 major networks. There's probably actually a lot more now, but this is an old question. And let's say we have 3 major types of television programs: drama, comedy, and reality. Now, this particular table is missing a few things. So ABC is missing its dramas, but we know that they add up to 20. So we can look at this. This is 15. So 20 minus 15 this has to be 5. And if we look at reality shows on NBC, that's missing, but 20 minus 12 is 8. Fox is missing the total, so that's 20. And now we see that ABC is missing the comedy, but we have 18 minus 10, which is 8. And now we see that CBS is missing comedy. So we have 30 minus 15 is 15, minus 10 is 5. And now we can find the total for the CBS shows, which is 17. And we can find the total for reality shows. 15 and 10 is 25. So now let's just check to make sure everything equals 75. 20 and 20 is 40, plus 35 is 75. 50 plus 25 is 75. So we filled in the table. So now we need to create a joint probability table. Now I'm just going to write these next to here. Now, the easiest way to do this, I hate that that clears every time. So the easiest way to do this is we can divide everything by 75 very quickly if we just create a list. So if we just create a quick list with all these numbers in it, 5, 3, 7, 5, 20. I'm just going to create one list. I'm just going straight across. 10, 5, 8, 30, 8, 7, 5, 5, 25, 20, 20, 17, 18, and 75. Okay, so now what I'm going to do, remember how to divide something. So we go over to list 2, we hit the up arrow to highlight list 2, and we want list 1 divided by 75. And we get all our answers. So let's write these in here. I'm just going to write them in here next to them. 0.067, 0.04, 0.093, 0.067. This is easier than, that's a 0, doesn't look like it. And 0.267. Okay, so this is 0.093. This one is 0.133. 5 is 0.067. Let's see, what's the 8? I didn't catch the 8. That is 0.107. 6 looks weird. Okay, and then 30 is 0.4. So 8 was 0.107. 7 is 0.093. 5 divided by 75, 0.067. 0.067. Well, I know 25 divided by is 0.333, right? It's 1/3. 333. So the 20, 0.267, 0.267. Let's see, let's pull this 17, I don't know. This is 0.227. 18 is 0.24. And 75 should be, and it is, 1. So we have all of our joint probability table created. So now we need to find the probability that the show is a comedy. So we don't go to the very first one. We go to the end. There are 30 comedies out of the 75. So that is 0.4. Find the probability the show is on ABC. So we go to the total of the ABCs, which is 0.24. Find the probability that the show is a comedy on ABC. So remember, these are marginals, because we just wanted to know if the show was a comedy, not that it was, we don't care what network it's on. This was also marginal. We wanted to know what was the probability that the show was on ABC. We didn't care what type of show it was. So let's find the probability that a show is a comedy on ABC. Now, to do that, we got to go the ABCs and the comedies, and we end up with this number, 0.107. This is the joint probability. So find the probability that a show is either a comedy or on ABC. Well, remember that we know that the probability of A union B, and or probabilities are unions, is equal to the probability of A plus the probability of B minus the probability of A intersection B. Because this gets counted twice, because this gets counted in all the shows that are comedies. So we're going to call this 0.4, plus all the shows that are on ABC, minus the joint probability, 0.104 or 0.107, because this 0.107 is included inside here and inside here. Because you'll notice if you add these up, you'd get 0.24. If you add all of these up, you would get 0.4. So this 0.107 is included in here and in here. So we have to subtract one of them back off. So we have 0.64 minus 0.107, which is, let's get our calculator real quick, 0.64, whoops, I don't want to be in there, 0.64 minus 0.107 is equal to 0.533. 0.533. So now we're able to find that union probability using our contingency table. So now let's talk a little bit about conditional probability. Now this is something that's kind of weird and different that you probably haven't seen much of before. So conditional probability is defined using the probability of A with a straight up and down line. This means given B. So this is the probability of A given that B occurs. So we think of this as maybe the fortune teller or whatever has said B is going to occur. What is the probability that A also occurs? So of all the outcomes which are in B, so of all the times which B actually happen, what is the probability that A happens also? And I say also, you'll see in a minute why I say that. Because if I already know that B's happened, I can't count outcomes that are A and not B when B has already happened. So I want you to think about this. Consider a committee. We have a committee of 5 people, 3 women and 2 men. One woman, okay, I have a typo there. One woman has a PhD, 1 man and 1 woman have master's degrees, and 1 each have BS degrees. Now that sounds really confusing, so we can make a contingency table out of that. We can say men, women, and we can say PhD, masters, bachelors. This might be a little bit easier to see. So 1 woman has a PhD, 1 man and 1 woman have master's degrees, and 1 each have bachelors. So that's what we're looking at. So now we can actually make this contingency table. This is 1, 2, 2, 2, and 3. So if a person is chosen at random, what is the probability that that's going to be a woman with a master's degree? So there's only 1 woman with a master's degree out of the 5 people, right? So that's just going to be 1 out of 5. So, but if a woman is chosen at random, what is the probability it will be someone with a master's degree? So we're given that the person is a woman. So we're only going to look at out of the 3 women. So out of the times when B occurs, out of the times when we have a woman, what is the probability? So here, this is the probability of a master's degree intersected with a woman. This is the probability someone has a master's degree given that they were a woman. So the woman is chosen at random. We know it has to be a woman for whatever reason. And so now we're only taking it out of the 3 women. So it's still 1 on the top, but now it's 3 on the bottom. So we're taking it out of a smaller group of people. And that is the biggest part of it. We don't want to look at the probability somebody has a master's degree because we don't want to include this man in there. He can't be chosen. He's not a woman. A woman was going to be selected at random. So this brings me to the conditional probability formula. You'll notice this top part is the joint probability or the intersection, because in order for us to say we want the probability of A given B, both A and B have to have happened. But we're taking it, instead of taking it out of all of the possible values, we're now taking it only out of the times, or the proportion of time, when B happens. So let's redo this previous example using this information. So knowing that we want the intersected probability, so if we do all these and we find joint probability table, this is going to be 1/5, 1/5, 1/5, 1/5, 2/5, 1/5, 1/5, 2/5. And then here we have 2/5, 3/5, and 1. So redoing this, dividing everything by 5, we know that the probability that someone has a master's and they're a woman, master's, woman, intersection is 1/5. And now, if we want the probability someone was a master's, intersection, they're a woman, divided by the probability that they're a woman. So we have the 1/5 divided by the 3/5. Oh, wait, these 5s can cancel, and we end up back again with 1/3, just like we did before, because the probability that someone was a woman was 3/5. And we will, of course, do more of these in class. So if you're kind of getting lost, we do much, much more of these. So I want to talk a lot more about this. This is something that really kind of starts to confuse folks. Out of all the women in the US, what percentage own a car? This is an example of a conditional probability because we're taking a subset of the population. So we want, what is the probability somebody owns a car given that they're a woman? Out of all the people in the US, what percentage of the people are women who own cars? This is an example of an intersected probability. What proportions of couches are red? So that's the probability something is red given that it's a couch. And here we have what portion of furniture are red couches. What's the probability that we have a red intersection with couch? What is the probability of someone contracting chickenpox after getting vaccinated? So the probability of getting chickenpox given that they're vaccinated. What is the probability of being any person who contracts chickenpox and got vaccinated? That's the probability of someone who has got chickenpox and got vaccinated. So here's a note. This is always more than or equal to the first marginal probability. So in this case, the probability of someone getting chickenpox given that they're vaccinated is more than or equal to the probability of getting chickenpox, which makes sense, right? Because this is taking it out of a much smaller group. This is taking them out of everybody, whether they got vaccinated or not. This is taking it only among people that got vaccinated. So in this case, what proportion of couches are red, given that it's a couch, that's more than the probability that of any furniture is red. It has to be, or it can be the same. If it's the same, it's independent, but we'll talk about that later. This is always less than or equal to any one of the marginal probabilities. So the probability that I get chickenpox and I got vaccinated always has to be less than or equal to the probability that someone gets chickenpox, which of course it is, because they're taking this out of the same pot of people, and much fewer can meet the criteria of two things that can only meet the criteria of one thing. Here they just have had to have chickenpox. Here they had to have chickenpox and have gotten vaccinated. So let's move on. Another example. Here's a joint probability of marital status and gender. So let's see what we're going to do with this. So let's find the probability that the person selected at random is a man. So the probability the person selected at random is a male. So it's the probability of S1. So we want over here, we want that marginal probability because we don't care about their marital status. So we want to go to the margin. What is the probability that a person selected at random is a married man? Married and a man. So that's an intersection. So we literally create our intersection, M2, yeah. And that comes up right here, 0.290. Now we want what percent of men are married. So for this one, we want what percent of men. So of men is your given event, S1. So what percent of men are married? What percent of people are married who are men, given that they're a man? Because we're only looking at the men now. So what we want to do is we want to look at using our conditional probability formula. We're going to take the men who are both married, or they're men and they're married, and divide it by just everybody who's a man. And I cheated over here. I get 0.6 or 60%. So 60% of the men, not mean, I'm used to writing mean, are married. So if you think about it, a lot of times I explain this to folks like this, taking all this off of here. I like to explain it this way. Let's pretend that you had 1,000 people at a party. Okay? We have a party with 1,000 people. 448 of them are men. 516 of them are women. And the question is, how many are married men? 290, right? So if I'm only looking at the men, I'm going to cross this off. I'm only looking at men. What percentage of the 484 men are married? Well, 290 of them. So 290 over 484, which is 0.6. So this is also a good way to look at it. Now, just because I want to, what percentage of married people are men? So what percent of married people are men? So in this case, we're only looking at the subset of people who are married. We're not concerned with the rest of this. So we're going to look at the ones who are men divided by the total, which I would be very shocked if that wasn't very near 0.5, divided by, 0.9 divided by 0.581, 0.499. So almost 0.5. So looking at this is very different. You can't just switch these around. Remember, this is the probability of married people. So given that somebody is married, what is the probability they're a man? So you can't just switch these. You have to be very, very careful which one you're doing. And the of is the given event. It's right here. And remember, the top has to be the intersection. I can't put the probability someone is married, because if you look at this, what if I did that? The probability somebody's married is 0.581. The probability someone's a man is 0.484. That would be greater than 1. And I know that would be wrong. Because if I'm given that somebody is a man, then they can't have been a woman. So I don't use those. So I'm only using this on the top, not this one. So that's really an important concept to get. And like I said, we will be doing much more of these in class. So this is a little shorter video. I do want you guys to also watch the Annenberg learning video for this section for 4.5 and 4.6. So today would be a good time to watch that. It will help you out with understanding. And who knows, there may be a quiz question about it.